Okay, straight away into the business. We try to define what is environmental engineering before we go on to the air pollution and things like that. Somebody might find this a little repetition because we normally talk about this thing in the first slide is typically this. What you see here is a great deal of technological development that has happened ever since the Industrial Revolution and things like that. And then to start with, we had the civil engineering, and you have all kinds of engineering now. Okay, and so much has been the development and the advancements that you have all kinds of the engineering breakups and things, the branches and sub branches and things like that. So you think of the mining engineering, chemical engineering, automobile, electrical engineering, and civil engineering and things like that. Okay, but all these technologies, all these developments have happened with just one simple objective in the mind: to make the life comfortable. Okay, and for the human society, that like you become more and more comfortable. Use the technology, you can do the things faster, you can do the things efficient, and as a result, lots of good things happen. Person can live longer, the health facilities are better, and things like that. Okay, this has given rise to the globalization. The communications have been good, the transportation has been so good, the comforts are plenty, and things like that. But having said that all, but if we go each one by them, like one by one, eventually this leads to some kind of a problem as well. Okay, we all know about that one. Okay, and the problem, we can go in details what the mining people will do. Harmful things. Okay, they will go down the underneath 3 kilometers, 4 kilometers, and if we can say that God had made everything under the ground so that it is not disturbing, the man has been able to bring it up. Okay, and then we have all kinds of problems that are coming up. Well, for good thing, but then again there will be some associated problems. We all can talk about new chemicals being added, the problem of pesticides. You can talk about the transportation, very nice. You can drive through the cities and the quickly can go. But then again, the issues and the problem that comes from the transportation and automobile engineering. So is the power generation. We're talking about all kinds of problems with the power generation, not only the SO2, NO2, particulate matter and things like that, but let's not forget even for the carbon dioxide. And so is the civil engineering and things like that. So what was happening when these things were all developing and things where people were very happy, and then you started seeing the after effects or the backlashes of the technology. Okay, everything has its good side as well as the bad side. So there were also the backlashes that started coming in. Then the people from the science and the people from the medical sciences and working on the environmental health, they came up and they said, well, there are certain problems. Things are not so perfect. And then these things, the way we are talking, the way we are developing, the way we are progressing, cannot be sustained. Impossible. I mean, you just can't go on expanding this. You can't go on increasing your mining area and making the extractions and having the product after the product. The way you just imagine. I mean, is it sustainable? The kind of the iron and steel demand that's going all over the world. Suddenly, the Chinese are growing 12%, India is growing 10%. And the first thing requirement is the iron, steel and iron and steel. Okay, because anything you want to build, the first thing required is iron and steel. And you see all kinds of international politics, international the companies, they're taking over the one or the another one, and suddenly issues has come up. Similarly, number of automobiles. I was giving an example today to some class as to number of automobiles in Delhi. Okay. I asked someone, is there any guess as to how many vehicles we might have in Delhi? More than 40 lakhs. I mean, they started with some 40, 45 lakhs, almost like 1,000 new vehicles are registered in Delhi. Apart from that, Delhi being in the center place, there are lot many vehicles that are coming in and going out of Delhi. From all adjoining area, from the, you can talk about Faridabad, you can talk about Noida, you can talk about Gurgaon and all kinds of things. Impossible to sustain. not only in terms of the infrastructure limitation, but from the backlashes, if I can use it. It's kind of unbridled, uncontrolled growth, just simply cannot go on. Similarly, this was one example which is very apparent, but that is true with everything whatever happening. Okay, and then if you have all these problems, this thing, the technologies or the engineering which came for being good for the human society, that started creating problem, and then it is not sustainable. It cannot be sustained unless the people, the science that we do, okay, and EM or air pollution or the water pollution, this came into being, and then that it encompasses the whole thing. It's just not here, or you can add on to many things. There could be 10 sub branches here, So this thing came into being, and then they said, well, all right, if you want the way kind of growth you want, there has to be something more you have to pay. And then here, what you see, the interesting point is you have a product here, or products rather, a product everywhere. But this is not an engineering that gives a physical product to see. All engineering gives you a product, a comfortable product, okay, to make you comfortable. But this science or engineering doesn't give you any product, okay, but it sustains all other products. Okay, if this wasn't there, I'm sure the bubble of being healthy, being wealthy and things like would burst. Okay, cannot be sustained, impossible. Okay, so this is how this came into being. And then you see here the kind of thing we are talking about. Okay, it cannot be a job of civil engineers alone, or mechanical engineers alone, or the person of hydraulics background. So it is the very subject of environmental engineering science becomes interdisciplinary, and that's how there are more and more emphasis on the interdisciplinary solutions. And the best person to clean your house is you yourself. Okay, I cannot come and clean your house because I don't know what's in your house, how the things are stored, and what is the best way. And your system should also work, and you should be able to clean it also. So what is happening is within this thing, okay, within this thing, the kind of environmental engineering that is developing. Okay, because a person he knows best about this, about his own product, because you want to continue the product, you want to use the product, but you want to. So as a result, has given a lot of within development of the clean technologies, if you like. But this is what is our job, is to sustain all these things. So we in fact are the engineering which are helping or making every other engineering survive. That's what is my interpretation of the environmental engineering. Okay, but the focus for this course will be, as you know, is air pollution. And then you see the fundamentals are very important. But this first lecture will talk about more of the atmosphere. Okay, stop me any point whenever if you have a question. So if you can read, we shall talk about the origin of the atmosphere, and it's very, very interesting how the atmosphere was created and what it was before and how it happened. And let's very quickly go through, because we should have the idea, the person who has lost the history and he has lost his roots, okay, he is unsuccessful man. So we are talking about the atmosphere, we should know about the history of the atmosphere. Leave aside the history of air pollution, but let's say how the atmosphere was formed. So the origin of the atmosphere, to start with, probably it was all hydrogen and helium, nothing else. Okay, why I say hydrogen and helium? First, the universe when it was created, okay, it is believed that largely the gases around the planet was hydrogen and helium, the most light kind of thing. And if still people believe, or what is the science that tells, if you go to Jupiter, for example, okay, still, because Jupiter is least affected because anything far away sitting in its corner, still full of hydrogen and helium. Okay, but change the style of life, things got changed. Okay, but then the air was like, air is sitting in such a middle place, in the universe, that you are not so hot, okay, like the planets which are close, nor we are so cold, like we are far away from the sun, that, well, nothing will happen. So such a beautiful temperature settings on the earth we have, that the many things happened on the earth. Okay, and the original atmosphere was then slowly it got stripped of the hydrogen and helium because of the solar winds, and it became very void of hydrogen and helium with time, of course. Okay, and then you see that, well, that's what it says, the hydrogen and helium have the smallest atom by mass, we all know that, and then it was very easy to drive them out. Okay, the early earth was not protected by a magnetic field also, so the removal was very this thing. Thus the current atmosphere is a secondary atmosphere. We started with this one, and the Jupiter is still what you can find the hydrogen and helium. Okay, things got changed. Okay, and then so we are no more talking about the primary atmosphere. It got changed, and got changed to something else. Okay, so we are talking about the secondary atmosphere, and then what is largely believed. Okay, it is the kind of atmosphere we have. The responsibility for the kind of atmosphere is from the degassing, okay, or venting of the volcanoes. Many things came from there, and that is the basic thing in the atmosphere, that has essentially come from there. Any idea what comes out from the volcanoes? SO2, yes. Not so much of hydrogen. CO2, huge amount of CO2. Okay, and so CO2 and huge amount of the sulfur dioxide, and there is significant amount of the, this is the typical picture that's coming out, the volcanic eruption. And then what you will find is, apart from the gases emitted initially, once the hydrogen, helium was gone, the gases in the atmosphere were similar to the volcanic activities that we see. There is a huge amount of water, okay, H2O, that anyway comes out, and CO2 and SO2 we can also see the certain percentage been given in, and apart from that there are other things also, little bit of, the sulfur, the chlorine, the nitrogen, hydrogen, and ammonia and methane. Okay, so again, what you can quickly tell, that this was not the atmosphere what we see today, and so this many things would happen even after this. Okay, so what do you think that possibly could have happened after this? Cooling is constantly going on. What would happen to the once we have the cooling? What will happen to H2O? It will start condensing, right? And slowly, that was the first thing that probably might happen, and that might have a little bit created the kind of waters in the oceans and things like that. Okay, and then, well, the CO2, something should happen to CO2 as well. Okay, we are talking about what kind of percentage of CO2 we are talking today in the atmosphere? 0.03%. Is that right? In terms of ppm, tell me. Okay, very good. So this was this scenario. And now let's quickly see as to what happened, because we want to move on to something else quickly as far as possible. Okay, the title you can't see is the modern atmosphere. We all know about this. We will not spend much time on that. Okay, this is the nice picture you see here, and that is fundamental to our survival. Okay, the water should disappear, nitrogen should come, the oxygen should come, and of course carbon dioxide is a byproduct. But the main thing is the oxygen. Is oxygen a product coming out from the volcanoes? No. So atmosphere has undergone very serious changes and very interesting changes. Now, so let's see what those changes were. Okay, now we can question ourselves, where did the oxygen come from? Today's oxygen we are breathing every moment. Okay. Oh my God, let's see what it shows. Okay. Now this is the comparison, you see. This side is what you are saying, the volcanic eruptions, and this is what is the modern atmosphere, and you see things are dramatically changed. Okay, very different. How this happened. At least we should always know the basics and the history how things happen, like. And well, of course, these are all theories largely believed to be true. Well, we don't know, but this is what is the science that tells us that probably this might have happened. Okay. Now we'll try to answer as to where did the all the oxygen come from, and then let's not forget where did all the CO2 went in. Okay. Okay. Let's talk about the water. So what we are talking about is the formation of oceans. Okay. And now what we are saying, the earth is cooled enough that H2O condensed to form the oceans. But the kind of the calculations that you can do, the water which probably, or H2O in the vapor phase that probably came out, was not as much as that it could create 2/3 of the land mass as the water and the kind of depth the oceans has. So that theory doesn't quite hold. So what is the other thing the people are talking about is estimates or the amounts of the H2O outgassed is not enough to fill the oceans. What is largely believed, it seems like that a large volume of the water was added by the impact of icy meteors. Okay, many of the meteors were like very icy, contain a lot of water. Some of the planets also contain water, and that came and hit onto the atmosphere of the Earth, and in the process also got condensed, because things will come, they lose the temperature and things like that. So largely that is believed the kind of amount of water that we have. And once you have the water, CO2 will dissolve. What is the law which governs the dissolution of gases? Henry's law. Okay. So that was one thing. But again, you can see that if I have like about 20% of CO2 or whatever the CO2 that was there, but it won't produce the kind of, it won't, that amount of CO2 that disappeared from the atmosphere would not disappear. Okay, because I have a huge amount of CO2, and that all CO2 will not disappear. Okay, so what would happen if I want to dissolve more and more? What should I do? I should consume it. Okay, then I can dissolve more and more and more, as long as I can drive out the CO2 from my system. Okay, and somehow use things. So again, these are the theories. Again, there's the kind of the knowledge we have that we are trying to answer that how the CO2, the kind of CO2 levels we have would have kind of achieved. So quickly have a look onto the things as to this is the life that was made. All these things, the kind of atmosphere which you see was possible because somehow, we don't know, the life came onto the earth, the spark which we talk about of the life, that somehow happened. How it happened, we don't know. But then if you look, essentially look, what are the basic ingredient or the building block in the life is what? Amino acids. Okay, and the cell. For to make the amino acids, what you really need is ammonia and some form of the ammonia, methane and water. Methane plenty from the volcanic eruptions, right? Ammonia, certain amount of ammonia also is water in the form of the water, not in the form of the vapor, right? So you had basically all these things happen, all things got dissolved into the water. And first, because you're talking about the ocean only, we're not talking life on the land, right? Okay, so when these things were there, these can somehow, okay, we still don't know how it happens, and we can't have the ammonia and CH4 and water and try to make like the life, it's not possible. Okay, but these can produce the amino acids, the basic building blocks, and probably most of you know the structure of the amino acids. Okay, then you have the amino end there. This is the side chain which can have something here. This is the alpha carbon, which is known as, this is the carboxyl end, and this is the hydrogen. Okay, and then the complex sequencing of amino acids gives us what? Proteins. Okay, and that's the basic building block. Okay, so probably that's what happened. So, and then what my picture probably should come up. Okay, and what you see here, possibly, like make the amino acid, nucleotides were formed, DNA, RNA, protein, and some kind of proto cells which we all now know actually what all are inside this one, and we thoroughly understand. And who's the one who invented or who talked about the basic living structure cell? Who was that scientist? Robert Hooke. Yes. When and how he gave the name, what he was doing was he was cutting the cork, the slicing the cork, and he saw the hexagonal structure, and then he said that's a cell, and that's how the cell was invented. Okay. So we are still, we should not forget we are talking about the atmosphere, and so possibly this all happened, and this little tiny thing, the smallest thing you can think of, this came up and then this could multiply. Okay. The basic definition of the living thing is that it is able to reproduce itself. Okay. That is a fundamental definition for the living thing. Okay. So if it could reproduce and multiply very quickly, that might have occurred, we don't know, under the primitive atmosphere or the hydrothermal vents or deep in the Earth's crust, but largely it is believed that it happened in the ocean. That's what is the first life was happened in the, and then the life, normally what happens, we need the life, you have the conditions to produce the life, but sometimes the life changes the very condition from where they were born. Okay. You had a different kind of atmosphere and it created life, and now the life becomes responsible to change the atmosphere and create another kind of life. Okay. And how it happened we'll see in a moment. It's largely believed that all this unicellular or the algae and that kind of thing, it occurred at some in the ocean or wherever there was some kind of places there could sit and grow. And you see here what would happen largely, they will consume CO2. Okay, CO2 and methane will be consumed. The CO2 will be coming and getting fixed in the sun. So as a result, more and more CO2 will dissolve in the oceans or water and things like that. And as a result, the activities largely which they'll give as a byproduct will be oxygen. Right? And there is no oxygen in the atmosphere, right? At the stage which we are talking about. But the CO2 is going on, CO2 is getting fixed, and as a respiration, the oxygen is the end product from here. So oxygen will be excess in the ocean slowly with time. The time scales we are talking, like billions of years. So this CO2 or this oxygen, that will evolve, okay, and that will try to come out of the ocean and slowly started building up in the atmosphere. So in a way we have said that, well, how the CO2 got into it, CO2 was consumed, more CO2 was dissolved, okay, and then the oxygen started coming out, and well, all things were happening. It is largely believed that even on the land, the plant life had started growing on the land slowly. So in the process, all the carbon got fixed in the plants, and then we all know the earth was very, very stormy, very dynamic, and many of the forests that were created or many of the biomass got subsided into the land, and everything got fixed, and as a result the CO2 is one which constantly went down, and the kind of levels of the CO2 that we have were eventually achieved. Okay. What it says with the evolution of the life, the first cellular organism, which is cyanobacteria, you all know about that because you have done the basic courses, began to use the gases in the early atmosphere, ammonia, methane, H2O, for energy, and that what I've said is the photosynthetic activities, and these organisms use CO2 and produce oxygen as the waste product. In fact, oxygen started as a waste product, and it is only we try to reason it out as to where the things are and how it happened. Okay. So let's go to the next slide. So we try to explain as to what happened and how it happened. So how that's where the oxygen come from and where did the CO2 go? We have tried to answer that. Dissolved in water in the oceans, used by the life by photosynthesis, and buried when the plants and microorganisms die. The source of coal and oil also becomes because of that kind of this thing. And why the hue and cry is that, well, we are using so much of fossil fuel that we are trying to build more and more CO2 again, the CO2 levels probably will not go to the kind of levels which were there in the beginning, but there are other issues which are, you are familiar about, the greenhouse gases and the earth temperature going up and things like that, but we won't talk about that. Look at the timeline. The earth is about 4.5 billion years old. Life first appeared in the ocean at least 3.5 billion years ago, and it's about 0.9 or 1 billion years ago there is enough oxygen in the atmosphere. So in fact it is largely believed that many of the species that were there on the land, the oxygen was very toxic to them, because like before the oxygen came, some of the life that was there, life in terms of the plants or whatever kind of bacteria or things were there. So there it became, like largely there must be anaerobic bacteria kind of thing that might have grown, and they could not sustain the kind of oxygen that started coming out. So but then you see the adaptation to the condition is survival of the fittest, that kind of thing, and that we all understand, Darwin and things like that. So there was a change in the lifestyle also, and the kind of the man and the life we see is largely because they could adapt and change itself to the changing atmosphere. And then from the harmful ultraviolet radiation, the sun, what it says, there is enough oxygen in the atmosphere to produce the ozone layer, and life can finally move onto the land. When we started having a lot of oxygen, what would happen? We didn't, to start with, we didn't have, we all know about that there is ozone in the stratosphere. How would that happen? Because we have lots of oxygen, and uncontrolled UV radiation that will reach onto the surface of the earth, okay, and these UV radiation, what they do in the stratosphere, how is ozone formed? Ozone is formed that oxygen is broken down because of the kind of radiation that were coming in the stratosphere to nascent oxygen. O2 is broken down to O plus O. This O will combine with oxygen to make ozone, right? So this, right now this is happening in the stratosphere, but in the beginning that was happening right on the stratosphere, and as a result slowly the ozone level went up, and we have the kind of a layer, or it envelops the whole earth as a form of the ozone layer, okay. And then so those radiations were stopped, so the kind of life we see here somehow cannot survive those radiations. So you see how over the period of billions of years how things got changed, and then we have the kind of atmosphere, ozone is sitting up there and things like that, okay. So this is how the kind of atmosphere you see. These are the basic people largely believed stories. And you see the other plant, Venus is very close to the sun, it's very hot at the surface, so water vapor in the atmosphere does not will condense. So I mean, we don't know if there is a life, but the possibility of the life is very, very low. There is a greenhouse effect, there is no oceans or rainfall, the CO2 whatever is there, it doesn't dissolve, so probably it is more or less stays what it is. But earth is very uniquely placed in the universe, and so are the life here, and so are we are talking and discussing and trying to sort our problems out, okay. This also is a Mars, little cooler than Venus, but it's smaller than Earth, so small that most of the atmosphere escapes into the space. There is no oceans or rainfall, so CO2 stays in the atmosphere. 98% of the atmosphere is CO2 there. It's large, because now Mars we know much better than what it was before. So again, there is no hope there, and so Jupiter is unchanged, and that's why it is largely believed when the Earth has just, or the universe, or the kind of universe which we see, or our solar system or our galaxy was being formed, so it was like hydrogen and helium. But things got changed onto the Earth because of our unique situation that we have, the moderation in the temperature largely, that made the things possible. Okay, very quickly, I mean, I don't want to read this one out, but you can all quickly see this one, and this is a summary of what we have talked about. Okay. If there are no questions, then let's go on to something else, and let's talk about something, we're still staying with the atmosphere. Okay, let's talk about few things in the atmosphere, and then what you see is the atmosphere is very, very small. Just to give a little feel, relative to the size of the Earth, the atmosphere is extremely thin, 90% of the mass below 16 kilometers, that we all know. Given that the Earth's diameter is so much, okay, kilometer, the atmosphere is about the thickness of the skin of an atom. Okay, just to give you a little feel as to how little are the things and the atmosphere. Now let's talk a little bit about the vertical structure of the atmosphere in terms of the pressure, maybe a little bit about the temperature. The gravity holds the atmosphere, no doubt about that. Consequently, the pressure for any area can be defined by the weight, that is force, okay, but divided by the unit volume of the thing. So this is a little picture. You say we can define the pressure. These are all basic things. All you have done is that we can define the atmospheric pressure. Top of the atmosphere takes the kind of force it exerts. Just take area of 1 meter square, and that's what is the pressure. Okay. But what is interesting is then it's not the integrated pressure that we are talking about, but what is to interest for us as air pollution or the atmospheric people is to see how the pressure changes with time, with height. Okay, so we'll quickly show that. We all know how the pressure changes. Okay, and then so what you see here is, I'm talking about Z or H. I should be okay, H, and all the definitions and the numbers what you see. Very quickly, if you have take the rho as kg per meter cube, g meter per second square, h as meter, does it come to the force by area? It comes. All right. If that comes, then it is fine. So unit wise, you can see here. And now what I want to do is define the pressure with respect to height. So I can make this as a differential equation using H or Z. We'll use Z, okay? And do what? Put a negative sign, right? Because the pressure is decreasing. All right, okay. So this is called hydrostatic law. You all know about that one. There's nothing new. That is also applicable in if the water is a fluid. Okay, and we are just extending this to the air. A change in the pressure is equal to the density times acceleration times the change in the height. Okay, a parcel of air is balanced by the upward and downward forces acting upon it. Okay, so that's what we're talking about, the stability of the atmosphere. What are the forces acting onto the particle in the fluid? Gravitational, buoyancy, and drag. Okay. So this is what is the thing. So we'll try to combine this with respect to let's get to how the things in a complete sense, that how it will change with Z, because here, okay, here this can also change, right, the density part. We'll try to remove the density out of here. So if you look, this we will use maybe hundreds of times universal gas law. Okay, PV equals to nRT. What is N? Or mole fraction, or whatever you like. Can I find out the rho from here and try to replace the rho? So what I do? Okay, I can make mistakes, so be careful. So can I say that? Is that okay? So we can say this as the, no? P by RT? Alright, thank you very much. Okay. This becomes what? P by RT. Okay. Can replace here. Okay. So then what I can do? Okay. What was about this thing? dP was rho G dz. Okay. What is that rho we got the rho form? Whatever. Please tell me. P by RT G dz. Okay. And dP. Okay. I can find out the pressure. Okay. Find out what will be the pressure. That will change as the height changes. Take any height initial condition as Z1, Z2, initial thing, pressure as P1, P2. And please tell me what expression you are getting. Okay, we'll take ln, okay, P2 by P1 minus 1 by RT exponential E, okay, G Z2 minus Z1. I'm sorry, because this is what is getting. Make it more simplified. P2 equals P1 exponential minus G upon RT is that right? Okay, very good. So the idea of getting this equation down is just to explain how exponentially the pressure will decrease in height. Isn't it? That we have from basic, high school physics, we could write this one. Okay, and that's what probably the next slide should be. Okay, so you can find out the pressure, and then always what you should do is not only you derive certain things, you should always show graphically. It's so important to get the feel, because more than the equation, the picture gives much larger and much better feel and understanding. So you see the picture coming up here as to how the pressure would change, okay, very quickly as you are as you go up almost insignificant pressure. Okay, any question that you have? Okay, let's talk about the okay, let's talk about the temperature. Okay, you all know that when we go up, what happens to the temperature? It decreases. Okay, Kathmandu is cooler than Kanpur, Shimla is cooler than Kanpur, and things like that. Okay, and that's how you have the the Himalayas would be at the top of the Himalayas will be much cooler and things like that. Okay, how tall is Himalayas or Everest? 884. So you will what kind of temperature you expect there? Around minus 40 or so, because somewhere here you are here, and then you bring it here down here. Okay, so this is what up to 16 to 18 kilometer we consider this as a troposphere. You all know about that. Okay, this is called tropopause. The temperature is not changing here, and then you see there is a rise in the temperature in the stratosphere. Okay, all our aeroplanes, okay, will be well within here. Is that right? Or can it be more than this? Can it be more than this? Probably not. Most of the flights will be like, how much is 40,000 feet at the most they go. So around 10 kilometers at the most they will go. But well, the other spacecraft and all, they move even further and things like that. But the pollutants, sometimes they travel back and forth here. Okay, it will be interesting to note that the ozone depletion we all talk about, things go from here, and some of the ozone is also contributed from stratosphere to the troposphere. That is the background ozone levels that we'll have. We don't know, we'll talk about this, but then as we go up, the temperature increases, and again it decreases, and again it increases, and goes infinitely very high. You're almost talking about the high temperatures here. We should know the reason. In this course, I'm sure not so much as to here, because we are dealing with the air pollution thing, and we are dealing largely within the 10 kilometer, and we'll derive an expression for this thing. Okay, and you will see with the height how this temperature will change. That we'll see later on. The mathematical part for the this thing was much easier, so I've done that. This will require some background at some point. We'll do try to give the how this temperature changes. We'll derive an expression as to how much this temperature changes. Now the question is, why should the temperature be higher or temperature should decrease with height in troposphere? And then it increases. Now albedo of Earth has nothing to do with this. Why is the temperature, forget about Earth, I am talking about suppose this reason, why the temperature should decrease? We all know decrease, and there has to be physics behind it, right? Surely has to be. Why? What is the relationship between pressure and the temperature? So what happens when the pressure is more? Temperature also. That is point number one. The other way you can look at the things is you need someone to absorb the energy, and once they absorb the energy, the temperature must go up. Where are the more, suppose in this room you are suppose 15, okay, the certain temperature. I make 100 people sit here, temperature will be more. Because maybe you absorb more, so there are more molecules here. Okay, so in fact these things are not heated by the air that is coming up. The radiation that goes back from the Earth, that is heating the atmosphere here. And then you see here there are not many molecules here, okay, of the Earth, of the air. So they are there, they will absorb more this thing. Suppose I have a steel plate in my hand, and then I have a source of heat. Okay, I put my before the heat plate. I have something else, so there is no rise in temperature. I put the heat plate. So many molecules closely associated. They have more numbers, so they will absorb more heat. Okay, then as a result, the temperature will be higher. And so, as you know, the number of the atoms and molecules of the air that will reduce. As a result, is the temperature decreasing, and then also the pressure is very high. And then, but if that is the argument, why would this increase? Precisely. Okay, and ozone absorbs, then as a result this thing will go. And then why should it decrease? Because as you go up, okay, after this one, there is nothing who can absorb the heat. But then again the question is why then it is going up again? We will see the reasons very quickly. Troposphere, the temperature declines due to the decrease in pressure that we have discussed about that, causing decreases in the average kinetic energy. Conceptually, the molecules of the air are moving around more slowly, causing temperature to decline. This can be predicted mathematically, that we will see later on in this course, but not now. Then also, the increasing temperature in the stratosphere has been mentioned. It absorbs the UV radiation. Once it absorbs the UV radiation, the temperature should be higher. And decreasing temperature in the mesosphere that we saw is caused by decreasing in ozone, because ozone has disappeared, because ozone layer is a layer. Beyond that again there is no ozone. So there is no one to absorb the heat. Okay, if there is no one to absorb the heat, the temperature should decline. And then in the thermosphere, why it goes up? Okay, the warming caused by the absorption of the UV radiation by oxygen. There is only that oxygen which is left on top of this, and that it is able to more oxygen in terms of the fraction. So it's largely the oxygen which is able to absorb even some more UV radiations, okay, in certain range. Okay, so that as a result in thermosphere you get even the higher temperature. So that's what is the structure. But you can write the mathematics also for this. That's not so well. It will involve something, but that is what we will not do right now. But that you need to do. The mathematics also can be written here. These two things, if you have to remember something, or you have to something learned by heart today, are the two equations. Because in atmosphere, pressure, volume, temperature are so interdependent, and we can really make terrible mistakes if we don't use them properly and correctly. Two equations, you don't need to give and define these two equations, but you should very, very clearly understand this. Okay, and we'll do some examples so that you are getting more used to these kind of things. Okay. Now I want to move to something, well, we might repeat it a little bit, now we are slightly from the atmosphere, we are coming to the air pollution. And what I want to talk to you is air pollution system. Or let's talk about the pollution system first. Pollution system. Okay. What I mean by the pollution system is systems is the certain components and their interactions. That's what the system is. We have a teaching system. So I am one component, you are one component. There are other things, like the visual aids are one other component, and we all are interacting. I'm interacting with that, and I'm interacting with you, and this is a system, right? So we have the system, and in pollution system there are 3 things, no more than 4 things. And entire environmental engineering is about just 3 things. There's nothing 4th thing that is in the system. Okay, and the system components are source of pollution, whatever that we are talking about. There must be a mechanism to transport. Okay, if there is no transport, pollution is happening, let it happen here. I'll run away from here and let the things happen. But the source, unfortunately or fortunately, it is transported. Okay, and then let it transport, who cares? But then it impacts someone so vital to us, and that vitality is, we call it in terms of the receptor. Okay, source, transport, and it impacts the receptor. Okay, you can talk about water pollution, you can talk about air pollution, you can talk about soil pollution. Okay, you can talk about noise pollution if you like. Okay, 3 components, very important things: source, transport, and receptor. And all the time that we are doing is studying this. Okay, there are sources, industrial sources, combustion sources, and like the wastewater generated, transport through the rivers. Okay, and somehow it is affecting the receptor. Okay, who is the receptor? We can see the little air pollution, source, atmosphere, receptor; soil pollution, soil, source, transport of the soil. Okay, that may be through the underground. Okay, and there is some receptor which we consider: noise, source, transport, receptor. That is all you are trying to do in any course in environmental science, engineering, anything. And some people will become expert for handling this, some people become expert handling this, some people are just onto this one, some people are expert on integrating these things. Those who are expert on integrating these things, who are those people? We all are environmental, but those who are able to integrate this, they are the modelers. They can model the things, they can model the system, and that is what is called system modeling. Okay. Those who are able to integrate this versus this versus this, it means they have integrated the entire system, and then they become the system modelers. Those who are dealing with air, they become air modeler, water modeler, soil modeler. We'll stop here. Thank you very much.